The last talk was on the LES simulation, large eddy simulation. Actually, the possible complexity of the object in LES is more complex than DNS, but it is still very simple. The examples of movies I showed you before is only the element of wing or box shape, or it is a simplified automobile model. LES is not popular. It is actually not popular in the actual designing process of automobiles, airplanes, and ships. So, what you will see as the result of CFD is usually simulated by Reynolds averaged Navier-Stokes simulation. So, today's talk is on Lance method. However, I remember I have to give you next homework because we have to complete simulation in this semester. So I guess you have already done the programming of convection term. The next step is not so time-consuming. You can, based on your experience in the previous work, you can easily get the structure of diffusion term. I will give you more advice after checking your previous homework result. And also, we have to consider the boundary condition of the velocity and pressure. I will give you additional information in the next class, but I'd like to set the deadline of this homework. When is the possible deadline of these two works? I guess it is 10th of the August, so how about 24th of this month? I guess it is reasonable, but it contains two subtopics, so I recommend you to finish the diffusion term in a week, and the remaining 1 week you should consider the boundary condition of velocity and pressure. So the deadline is it is 24. The Tuesday, 24th Tuesday. Okay. I give you some basics of diffusion term in the last class, and for the structure of boundary condition, I think you should make one subroutine. In some cases, we will make several boundary condition routines. One is, for example, one is for velocity and one is for pressure. but in my experience, it is very complicated because one boundary condition is in a routine and some other conditions are in the different routine. It is it is not easy to handle such kind of situation. So please provide all the condition in one routine. I will give you one example in the next class. Then today's topic is runs simulation. We call it RANS. It is abbreviation of Reynolds Averaged Navier-Stokes model. So some people are using L, R, and non-capital A and capital N and S, and they are the meaning of these two are the same. But I prefer using this one because R and N and S, these three are for these three characters comes from the name of researchers. So they should be written in capital letters. But A is not, A is from the average. So I prefer this one. But naturally, some researchers use this one. And there are some related abbreviation of method. Basically, a RANS method is for steady flow, but it is extension is possible for unsteady flow problems. So some researchers use this one. U-RANS, it is the abbreviation of unsteady Reynolds averaged Navier-Stokes equation. The difference of RANS and the LES method is basically its concept. Sometimes their appearance is very similar. The basic concept of large eddy simulation is filtering. It is filtering in space. But the RANS concept is basically comes from time averaging. It will be discussed today. But sometimes the situation is somewhat complicated. Sometimes we will use spatial averaging and sometimes time averaging in RANS method. The concept of Reynolds average, this is introduced by Osborne Reynolds. So it is this is the basic idea of the founder of this research. Osborne Reynolds, he died 1912. So it is already 100 years passed from the death of his work. His concept is decompose the flow field into steady part and fluctuating part. This is original flow field. If it is turbulent, it contains base 1 and fluctuating 1. If you get time averaged part, if you get time averaging, it can be decomposed into time averaged part and other fluctuating part. The definition of time averaging is basic one. If you have the extreme of integrating, if you get extreme condition of infinite scale of averaging, it will be a mean value. It will be mean value of the flow field. You can consider phi as u or v or w component of velocity and pressure and any other components in the flow field. So the consideration is like this. If the flow is steady turbulence flow, as I repeatedly said, turbulence is basically fundamentally unsteady phenomena. But if it is steady, the averaged value of the flow exists. So U bar indicates the mean value of this fluctuation, and remaining small amplitude fluctuations is now called U prime. This is for steady turbulent flow case. And there is other situation. Although the flow is turbulent, it has some tendency of decreasing or increasing. In this case, we will use a finite span of time integration in the averaging process. So it is between the unsteady and steady consideration. But the situation is the same as in the large eddy simulation. Time averaging does not appear in the actual calculation. The time averaging is used when we construct the model of turbulence. So the situation is written like this. In unsteady flow, we will change the basic idea of time averaging to ensemble averaging. So it can be called unsteady large Reynolds averaged Navier-Stokes equations. In this case, we will select the number of elements in the flow field. So this consideration is very similar to the filtering of large eddy simulation. We can say it is almost the same. In this case, N is the number of members of the ensemble averaging. But you have to, although this averaging does not appear in the numerical treatment, you have to keep this concept in your mind to understand what is going on in the simulation. In this case, the size of averaging must be large enough to eliminate the small fluctuations. But if it is too large, it will hide all the motion of the flow. So it is not reasonable. So we have to consider the the specific length of averaging in the when we consider the simulation result. The concept of constructing Ran's equation is this one. If we have fluctuations, by definition, the time average of fluctuation is equal to 0. So this product of two components, in this case, one is u component of velocity and the other is scalar quantity in the flow field. You can imagine pressure or density or any other materials in the flow field. Since it is in turbulent flow, both these components have steady part and fluctuation part. So the average of the product will be like this. You can easily calculate the product of these four components. But the UI, the average of UI prime times phi bar will be 0 because in this case UI prime times phi bar also UI bar times phi bar. In the assumption, in the definition of fluctuation, average of fluctuating part is equal to 0. So this one is 0, and also averaging of this one is 0. So the remaining part is only the product of averaged component and product of average of the product of fluctuating component. The important thing is this does not that we cannot delete this one. If UI and phi does not have any correlation, we can delete it. But in general, this does not. We cannot delete this one because sometimes these two components have correlations. Most important correlation occurs in the product of two velocity components. I think considering this one is better because if you assume velocity is composed of u and v component, it has u fluctuating component of u prime and v prime. In turbulence, we know this is not equal to 0 because if b prime is positive, it indicates it works to lift up the low flow velocity in the bottom of the boundary layer. So in the turbulence, in the situation of turbulence, if v prime is positive, it has some tendency of u prime will be also positive. And also, if V prime is negative, it indicates fluctuation of going down. It indicates higher speed velocity will goes into the present place. I'm sorry, this situation is reversed. In this case, if V prime is positive, slow flow particle goes up, and if V prime is negative, high speed flow particle is going down from the upper position in the boundary layer. So this situation occurs in the turbulence flow. Although each components are fluctuating, the product might not be zero. So in many cases, we have to consider this part. So in this case, it indicates two possible non-zero values of averaged products. One is Reynolds stress, and the other is turbulent scalar flux. At present, we do not specify what is phi, but you can put any components of flow field. This discussion is required in the later work of Ran's method. In the later discussion, we have to introduce turbulent quantity to simulate the behavior of turbulence. In this case, some physical component phi is transported by a flow field. I think this it looks similar to the construction of LES model. If you omit these bars and hide this part, this is equivalent to the Navier-Stokes equation. If we make the time average of all the continuity equation and Navier-Stokes equation, it is this type of equations. The important point is the same as in the constellation of LES model. There is remaining part. This is one additional component appears in the convection term. In this constellation, we will call the situation. It is this equation is not closed because it contains unknown parameters. Actually, we have in three-dimensional case we have four equations. This part is only one equation, and the second one is this is vector form equation. So 1 plus 3, so we have four equations, and unknown variables are three components of U and one component of P. So the number of equations and unknown variables are the same if we do not have this part. So if we can delete this one, this equation is closed, but we have new one. So this equation can be said it is non-closed equations. So what we should do is to have closure equations for this Ran's treatment. Before going to the closure consideration, the definition, we have to check the definition of these equations. In this equation, tau ij is written like this. So this is only for the tau ij is introduced only for the convenience of the of writing. It is stress tensor of mean flow velocity, mean velocity field. If we consider the transportation of scalar value phi, it can be written like this. Since the consideration is on incompressible flow, or rho is constant, so it does not subject to the time averaging. But if you are interested in compressible flow simulation, you have to consider the fluctuation of rho and average of rho. But in this case, rho is constant, and phi, the mean value of phi is transported by a mean velocity field, and it will be subjected to diffusion. The diffusion coefficient is not specified yet. If it is some chemical quantities, it will be this part will be determined by the molecular interactions. The point of this equation is this part. As in the Reynolds stress, this part shows the effect of fluctuations. The fluctuation does not appear in the average to flow field, but this part should be evaluated by modeling of fluctuations. It is now disappeared in the process of time averaging, Reynolds averaging. So the consideration is for how to close the equations. So we call it turbulence models as closure models, because it will add other consideration and to satisfy the equation. The basic knowledge is this one. Closed set of exact equation is impossible. At present, it is true, but as a scientist, you have to think there is no impossible things. So there might be a genius who can find exact treatment of this one. But at present, in the textbook, they say a closed set of exact equation. Exact solution of turbulent is considered impossible at present. So we need approximation of Reynolds stress, and for other terms appears in the Reynolds averaged equations. The first one is First requirement for the consideration is eddy viscosity model for Reynolds stress. The equation is exactly the same as in the large eddy simulation. This part is Reynolds stress, and we assume it is proportional to the strain rate of the mean flow. And this part is for the for correcting the terms. K is the kinematic turbulent kinematic energy. And this is for the consideration of moment, and also if we consider the transport of a scalar quantity, we will the assumption is like this: the turbulent transportation of phi is proportional to the gradient of the scalar and proportional coefficient of proportional relation is this can be called turbulent diffusion coefficient. In this case, we have to determine this part based on the characteristics of phi in later discussion. The definition of K is 1/2 of the ui prime times ui prime. This description is based on the Einstein rule. So if the same index appears here, it can be written as the summation of the square of each component, like this. Do you know Einstein rule of the? I guess you have to check the some textbook or internet information for checking the rule of Einstein. It is only for the convenience of writing. We have to. I will show you some treatment of closing. I guess it is. I will introduce 3 models. This one is the simplest one. The name is mixing length model. It is very simple, so the possible situation is limited. The new mu t turbulence viscosity coefficient is proportional to the density rho and the velocity scale of turbulence and length scale of the flow. This form comes from the discussion of dimensions. And what we have to do is to provide the value of coefficient C mu and the scale of L. Q is, the definition of Q is square root of double K. So the dimension of Q is equal to the velocity. Since definition of K is this one. In this definition, K is turbulent kinematic energy per unit density. So this one, the dimension of Q is the velocity. So this relation indicates eddy viscosity will be determined by the length scale of L. So the image of this model is if it is in large vortex motion, the mixing length is large, and the turbulent effect is not significant. In large vorticity, there is no strict definition of L, but so this is only an image for understanding, and there will be small eddy motion, and in this position L is small, and you have to increase C mu to indicate the increased turbulent effect for the treatment of Lorentz equation. This is small, but K should be determined by the assumption of it is Q is proportional to velocity gradient, and we have to define the function L. L is not constant, so some consideration is required to determine this one. This is a kind of zero equation model. Why we call it zero equation is because in later discussion there will be one equation model and two equation model and other model. Since this one is one of most simplest solution, it does not require any additional transport equation. So we categorize this one as zero equation model. As I said, it will work in very simple flow situation, like flow in two parallel plates, or flow in tube, but the application is very limited. Application is limited because the model depends on the flow characteristics of flow. So in many practical applications, characteristics of flow is different based on the position in the computational domain. So if we have to use this model, we have to determine C mu and function of L in each position of the flow, considering the situation. So it is not applicable for the complicated flow condition. Then what we have to do next is to introduce additional transport equations in the Lorentz solution. in the mixing ranks model, we have to determine this one. But if we can provide additional equations, it will provide more sophisticated, more accurate evaluation of turbulent effect. Actually, I will introduce two additional equations of transportation. The first one is turbulent kinematic energy K. This can be derived directly from the Navier-Stokes equation. But I learned the derivation of this equation when I was in graduate school. It requires 10 pages by writing by hand. So I will show you only the result. The basic procedure of deriving this one is to make this pattern from the original Navier-Stokes, from the original Navier-Stokes equation. It is multiplying component to the original Navier-Stokes equation. And integrate this one. It will lead to I think the detail, I cannot remember the detail, but the basics is multiplying UI component and integrate, and as you can imagine, it will produce this component. So after you get the equation of K, it has the form of the transport equation. The value of rho K in this form, this equation can be interpreted as it is transportation of turbulent kinematic energy by mean flow field. K is transported by a velocity component uj bar, and also K is affected to diffusion. This is a gradient of kinematic kinematic energy. So in this part, high turbulent energy will be transported to low turbulent region by molecular viscosity. And so this coefficient of the diffusion is molecular viscosity. So this value is very small. And other components is this one is turbulent diffusion. This is uj, ui. So this part is kinematic energy, and kinematic energy is transported by a fluctuation of velocity components. So it indicates turbulent is transported by a fluctuation. So fluctuation is transported by fluctuation. So the appearance is somewhat complicated, but we can assume this one is proportional to the gradient of kinematic energy. And in this case, the diffusion coefficient should be modified to include the enhanced enhanced transport characteristics of turbulent. So in this model, the coefficient is written like this. And other part, this one is rate of production of turbulent kinematic energy. This is the appearance is product of Reynolds stress and velocity gradient. It generates the new kinematic energy in the flow field. And this one is the meaning of this term is not clear yet, but it will be used in the next transport equation. This part is called product of this part is dissipation part. It is the square sum of velocity gradient, and this part is mu, not the kinematic viscosity nu. So this is dissipation rate multiplied by a fluid density. The detail will be in the next slide. The effect of this term is the conversion of energy from the turbulent motion to the smaller scale motion. It is molecular motion. So in this term, turbulent energy is going to heat. So it can be said it is irreversible conversion to heat. So this equation is complicated, but it has basics of transport equation. It has convection term and diffusion term. Diffusion caused by molecular viscosity, and this is additional diffusion caused by turbulence. And this one is production, and this one is dissipation. So in this equation, kinematic energy of turbulence is created and transported by flow and diffused according to molecular viscosity and turbulence, and it will disappear, dissipated into heat. One equation is not enough to calculate the turbulent viscosity because we have to consider the length scale of the turbulent. For this purpose, there are some possible structure of the model. So actually there are many models for this purpose. But one popular choice is turbulent dissipation dissipation epsilon. So we will compose the second transport equation of epsilon. Epsilon is transported by mean velocity, and it has production part and dissipation part and diffusion part. The meaning of epsilon is the dissipation rate. The definition is power, k power of 3 halves and divided by L. Why this selection is appear is because the counterpart of the transport equation is k. It is the energy. So possible counterpart equation is its dissipation. So by considering epsilon, we can check the balance of turbulence energy. As I said, the transport equation of K includes the production, diffusion, and dissipation, and in it the K should be balanced with the energy dissipation. So considering dissipation, considering transport of dissipation is one reasonable choice of selecting the closing model. However, the equation of dissipation, it is more difficult than the derivation of the previous equation of K. So the textbook of Farziga also said we have to. It is better to consider this one as a model, not the direct derivation of the direct derivation from the Navier-Stokes equation, because it has many assumptions already. If we get the solution of K and epsilon, we can get the turbulent viscosity mu T as the product of C mu and square root of K. No, I'm sorry. This one is original definition of Reynolds averaged equations. In K epsilon model, the turbulent viscosity is written as this. In this case, we have the exact value of K and epsilon. So in this case, C mu can be constant value. The change of this part is included in the already considered in the transportation equation of K and epsilon. So the present model, the name of the present model is K epsilon model. It is, I think, it is most popular model in the Reynolds averaged equation solutions. This shows one example set of model parameters. Actually, if you will use commercial CFD applications, it shows selection panels of these parameters. So the existence of selection indicates these parameters are not independent from the characteristics of flow. If it is near the wall, you should choose this value. If it has the effect of buoyancy, you should choose this one. So in commercial applications or a textbook, there will be some recipe of these parameters. So the knowledge is not clear in K-epsilon model. It requires some empirical information of these parameters. But in some cases, they are already validated based on experimental data. It has the actual usage of K-epsilon model requires further discussion of boundary conditions. Now we have two additional flow quantities. So we have to solve U, V, W, P, and K and epsilon. So if it is three-dimensional flow, we have to solve five flow components. And also we have to set the boundary condition of epsilon and K. K, the original source of K comes from the inlet boundary. If it is natural wind, there is already a turbulence in the natural wind. So the difficulty is only on the boundary wall surface. As in the consideration of damping function in large AD simulations, turbulent kinetic energy on the wall is equal to 0. And however, turbulent dissipation, it is not 0 on the boundary. So there are possible boundary condition of epsilon. In textbooks, the description of this part is very long. So if you have some problems to solve, you have to check what condition is used, what condition is reasonable for the object you have to evaluate the flow pattern. As I said, K-epsilon model is only one of possible choices. So there are many selections, but as I said, K-epsilon model is most popular one, and the second one is K-omega model. Since basics is almost the same, I will show you only the structure of the equations. K-omega model is in the textbook. I found that K-omega model is introduced by Safman, and later it was developed by Wilcox and Menta. I know only the name of Wilcox and Menta. So in this case, equation of transport equation is for k and omega. And definition of omega is, I'm sorry, I forgot to mention the definition of omega. Omega is the inverse of time scale of turbulence. Small vorticity indicates small time scale. So in this case, omega is large. Large omega indicates small scale motion. So the definition is inverse time scale of turbulence. So it is related to the scale of turbulence in wide range of cascade. The situation is the same. It has a convection part and production part and dissipation part and diffusion part. And it also has a basic parameter of the model. The knowledge of k omega model is slightly small in comparison to k epsilon model because this is a new one. But it has it shows good performance, especially in the solution of separate flow. If we have to evaluate the evaluate the separation properly, we have k omega model is a good choice. It happens when we consider the high angle attack of wing or transition from laminar flow to turbulence. The flow pattern subject to the separation of the flow. K epsilon model is not good at to reproduce the natural separation pattern. I will summarize the Lance model I showed you. In large categorized, Lance model has eddy viscosity model and Reynolds stress model. Eddy viscosity model is, as in the name, it determines nu T, turbulent viscosity. The mixing length model is the simplest one. It does not require any additional transport equation. And famous zero equation model is Baldwin-Lomax. I will introduce this one in the next class. And there is also one equation model. Sparat-Anomalous model is famous, but I will omit this one. The famous one is mixing length theory as a basics, and practically a popular one is k epsilon and k omega in the present situation. The last one is Reynolds stress model. This one is more complicated, so I will convey you only the image of this treatment. In the previous model, we consider eddy viscosity like this. eddy viscosity is a scalar in the previous k epsilon and k omega model, but in the analysis of experimental data or analysis of DNS result, we know nu t is not a scalar. It has some structures, and we have to consider eddy viscosity as an isotropic tensor. So it has 9 components. In this consideration, the solution is to consider transport of Reynolds stress itself. So the image is somewhat complicated. We will consider transport of all the components, Ui times Uj. Actually, it is tensor and 9 components, but it is a symmetric tensor. So the required solution is 6 components, because if it is 3-dimensional tensor, if it is symmetric, we have to use diagonal 3 components and off-diagonal 3 components. In total, 6 components should be considered. So the equation is written very simply, but this information contains six transport equations. As in the equation of k and epsilon and omega, this also has production terms here and dissipation terms here, and this is a new term. It is this part is actual structure of this part is like this. It is a production of pressure fluctuation and strain tensor. It will redistribute the kinematic energy to other component. This one is diffusion term because it has this diffusion coefficient, and the structure is similar to the previous diffusion term they appeared in k, omega, and epsilon equations. What we need in Reynolds stress model is somewhat complicated, but it will evaluate realistic turbulent structure. Actually, it also requires transport equation of epsilon. So it requires higher cost of computation. The simulation should be done on U, V, W, and pressure, and additional 6 component of stress tensor, and also epsilon. So it requires 7 additional transport equations. So if other turbulence model does not work well, the remaining choice is Reynolds stress model. But it requires 11 transport equations. So the cost is significantly higher than laminar flow simulation, laminar flow Navier-Stokes equation, Navier-Stokes solution. Okay, this is the end of the present class, today's class. Thank you very much.